Okay, so welcome to the class on Introduction to Computing. The beginning of it all, when we talk about the idea of computing something, we talk about software. So the question is, where does this software exist? Is it just an ethereal quantity which is unreal? Hold that question in your mind. So, what happened is, at one point of time, the number system that we know of, that is the decimal number system 0, 1, 2, 3, dot, 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 it just happened that English mathematician called George Boole gave a new representation which said that any given number can be expressed as a combination of two states. This was back about 400 years ago, perhaps, or 1600s, 1700s. It simply states that if this is your code, 1, 1, 1, 1, 1, 1, whatever you see here, this particular number can be expressed as 2 raised to 0 because it is the 0th place, and this one is 2 raised to 1 because it is in the first place, 0, 1, 2, 3, 4, 5, 6. And if you would use it as a code, expressing it as the power of 2, where the power is the placeholder, you would end up with a certain number. So it turns out that any given number that you have can be expressed as a binary number with this formulation. So a sequence 1 7 times, 8 times, starting with 0, would represent this number. Another example below here shows that a sequence 1 0, or read like this, 1 0 0 1 0 1 0 1, would give you another number. The beauty of it is, because it is now being expressed as two states, the state of 0 can be expressed as a state of no energy. The state of being 1 can be expressed as with energy. Now this energy just happens to be the presence of an electron. No electron, yes electron. Using just the combination of no electron and yes electron, they created something called a flip-flop. So a combination of setting and resetting between this holds different combinations over here. It could be, if there is no power at all, it could be a 0 and a 0. If there is any power at all, then depending on the combination of which one is negated and which one is not, you will have combinations such as 0 0, 0 1, 1 0, 1 1. If you use many combinations of flip-flop, you'll end up having different numbers, as you can see here. Now this, what you're seeing, is the fundamental unit of memory. This is where everything gets stored. This is how everything gets stored. So after having understood what is the fundamental unit of memory, just imagine a million trillion flip flop like this embedded into a chip, and with that a processor, and that will give rise to your hard disk, EEPROM, RAM, cache, all those memory devices that you have. So the question of whether a software is an ethereal quantity, which I said, pull the thought, right? So the question is up to you to decide, because eventually all memory is actually built on two states, no electron and yes electron. Okay, the presence of an electron is 1, there is no electron flow, there is no current, so that's 0. So you need power to hold some memory, but in certain cases there are certain devices which, once you embed memory, it will stay forever over there as long as the state of that semiconductor is intact. Properties of semiconductor is intact, so memory stays forever, right? So this gives us the connection to understand the von Neumann basic structure of a computer, which has memory. There's a control unit which controls the signal flow between the memory and the one which computes, the arithmetic and logical unit. This is basically the simplest computing unit that you can imagine, which actually consists of a microprocessor. So if you really want to, or are interested in understanding what a microprocessor is and how it works, I would suggest follow the book called Notes, Art of Computer Programming, right? This is the book. Probably the best book written on the fundamental idea of how computing happens. It's a very complicated book, but very, very well written. So somebody who wants to really understand what happens inside can go ahead and get a copy of this book any which way you can, your library or a hard copy which you want to buy. Well, so arithmetic and logical unit has an input which it takes and an output which it gives. That's what it does. It computes depending on what program is fed into it, what it is supposed to do as its own, and give out an output. Now the whole thing is could be a microprocessor, the whole idea, because it's a computer and it has all the important stuff where you want to store some data that you're giving. Input data gets stored over here. There's a control unit which controls the bit, the clock, the frequency of what this processor is capable of. Then there's the logical unit which knows what is the basic arithmetic, the decouplers, the demuxers, and all of that, right? All of that combined together makes a computer, a simple small computer. Now the computers that we have even on our smartphones are very complicated. Now let's look at what is that complicated structure. This again is a very simple representation. What we have here is the hardware. Some examples of hardware: a printer, a monitor or a computer, a headphone, the mouse, your USB drive, memory stick, keyboard. Now if all of these have to be connected to the user, there's a layered connection over there. At the core of the hardware lies something called kernel. This kernel is the one which talks to the hardware. It's somewhere over here between and the device drivers are the ones which are those specific softwares which knows exactly what to do with the signal that comes from a mouse or what to do with the keypad signal that comes from a key. So these are device drivers. They drive the operation of every device, because every device has its own way of functioning, own reason to exist. But of course, this whole unit, this whole input has to be operated and used by the user. So when any user uses this, there's a device driver which knows what has to be done, because based on the input that is coming in, the device driver will react to it. Between the user and the device driver, there are two more layers which you can see here. One is the operating system. These operating systems can be any. If you're using a smartphone, it's either the Android or the iOS operating system. If you're using the desktop PCs, it's Mac or Windows, or of course the best one of it all, Linux. Okay, so this architecture and all the things that we observe today has been developed. The first one to be developed was Linux, a very powerful and compact and very well organized operating system, Linux, and all others are just versions, newer versions change. A Linux with a grand user interface came out to be as the Mac and Windows. Well, so the way to get anything done on a system, because if a computer has an operating system, there's nothing much you want to do with it. It's just an operating system to handle all these device drivers and the hardware and stuff. This is just the operating system. Okay, but why you use a computer is because you want to get certain things done, like you want to browse, you want to check your emails, you want to write something, and maybe create a movie, write softwares. So all of these are applications. Your Anaconda software that you are going to install or probably have installed already is also an application, and it exists on the application layer. Now the user interacts with the application. The application has its own drivers which is handled, and the software, the operating system knows that this particular application can talk to me depending on whether the operating system is an Android or iOS or Mac or Windows or Linux. Depending on that, there will be certain adapters, layers that will enable the user to engage the application, and whatever you do here, eventually the computation has to be solved by the hardware layer, because you type in mail, it goes to the keyboard, then the device drivers know what's happening. It takes the permission from the operating system that this is a registered device, so we need to compute it and return the input to the user. So the whole operation is this. So if there are other layers, the other detailed block diagrams, which if you are interested you can go and check, but this is where the context is. This is how a software exists for you. So depending on what kind of a engineer you are, embedded engineer, you will be writing device drivers and handling the kernel. If you are a system engineer, computer systems, so you would probably be in operating system as well as the device drivers area. And if you are an application program engineer, then you have your own unique solution of getting things done. So probably you'll end up writing newer applications, newer pipelines, depending on what you want at this particular layer. So at every layer, there are certain default knowledge that you need to have. If you want to be embedded, you need to know about the microprocessors, the basic architecture. If you want to be here doing something with the core system, then you need to know about the concepts of operations, the operating system. So this is what a computer scientist, the computer science engineer is supposed to know, and that's what they study over the 4 years. Each layer, exactly what they stand for, and there are a zillion protocols for interaction between each, which has evolved over time. So That's fine. We are not here to do that. The quintessential thing that goes on while developing anything over here is you need a language to program, a programming language. So there are different kinds of programming languages for each of these layers. Let's check them out. The types of programming languages. The lowest level of them all, the lowest level language, which uses just ones and zeros, it's called the machine language. Eventually everything gets converted to the machine language. Nobody codes it. It's usually already, it has certain adapters which the assembly language uses, the mnemonics over here, which gets converted into the machine language. So this one pretty much is already sealed. You don't really program using these things. If at all you want to do any embedded programming, you will be using certain assembly languages to address the hardware level protocols and get the work done directly with the hardware. Now there is a next level, that's a mid-level language, so which sort of is a higher level language and has the data types and the variables which is more easy to relate with. So that is the middle level language, and the C programming language is a step up from the assembler, and this has been the go-to language for a long time. There is embedded C, there is object-oriented C. There are many different kinds of variations of C language. It's very powerful, and it is, since it is really very deeply connected and as the next layer to assembly language, the performance of this language is fast. I mean, you write anything in C, the execution of that happens very fast. Now there are high level languages. Usually the base layer of these languages are written in C itself, because when you create a language, you have to make sure that the machine eventually understands what you are writing. So there are layers, and usually the core of those layers will be written in certain standard languages, and you don't have to worry about it because this is just for reference, that you know the whole story and how it works. So the high level languages that we have, predominantly very famous in the world: C++, Java, C#, Python, Ruby. There are many more right now coming up for different reasons altogether. So you can check out some literature on different kinds of programming languages and what they do and stuff. But however, these languages are of two types. We'll understand what kind of languages. In high level languages, there are two kinds of language based on how they are computed, right? So we'll understand that. Well, having said that, so all of this, eventually all languages over here requires is actually created to do something, to get some automation, right? Some automation. And automate what? Certain things about the information. Everywhere that information is nothing but data. A structured data which has something embedded real in it is information. So as you see, everything here is structured. Machine is a very structured entity. So while you give information for the machine to automate, even the way in which you give should be structured. So that is data structures. Very, very important to understand, because if you don't understand and appreciate the meaning of data structures, then you will not be at ease when you program. You will always be confused. Once you understand the way in which the computer understands and appreciate it, that yes, this is the right structure which goes in, then things get easy because it gets organized in your mind, and you will now know how to address each of the structures of information. Now, the structures of information predominantly are of two types. One is primitive, one is non-primitive. Primitive ones are the ones which are the naive core component of any information, that it can be an integer number, it can be a decimal number which is called float, it can be a set of characters which is called string, and it can be a logical unit like yes, true, or false. That's a Boolean logic. So these are the primitive data types. Now you can just take for a moment, pause it and stop and think that any given data will usually be consisting of these. It can be a number. Numbers can be of many types: floating point with decimal, or just an integer without any decimal. Or the data can be probably your name, which is again a set of strings like text data. That is represented as the strings. And when we say integer, so which means that there is a proper understanding of what an integer and how much memory an integer is supposed to hold, how many bits and bytes, and the operations that it can perform, what kind of arithmetic and logical operations you can perform on integer, and how does it happen. All of that information is fed already into the computer. The computer understands that when you declare something as an integer, this is what I can, or the computer can do with it. Similarly, of course, the data, if it is just this much, it's easier, but information, the structured information from the real world, and the kind of automation that we are required to are much more complex. So there are certain non-primitive data types which are again classified into built-in and user-defined. The built-in ones are if you have a set of same kind of data, which are, let's say, a set of integers, a set of strings, you can use them as a list. So it's a structure, it's a built-in structure. It's called list. Then there is another built-in structure called tuple. Each one looks like a collection of objects. Set is a collection, tuple is a collection, list is a collection. But there are certain attributes associated with it. What you can do with list, you cannot do with tuple. And what you can do with set, you cannot do with both. There are reasons for it. So you may feel that any collection is just a collection. So you may feel that you can either declare them as a list when you input it, or a tuple, or a set when you input it. But you should know the meanings, the differences between these, so that you can efficiently allocate the kind of memory that you would require for the structure, the data that you're sending in for computation. And there is also something called a dictionary, and dictionaries we'll understand. Okay, so each one of these has certain features in it, and rightly so. When you understand that, you will realize that it cannot be any different. It has to be this way. Okay, so that's what you're supposed to get at. So final appreciation is that this differentiation becomes obvious to you. Well, user defined, built-in is this. User defined also in fact has a built-in structure. The system knows that this particular stack is a certain way it is. The system actually knows it. So you can actually debate whether it is actually user defined or a built-in. Some aspect of it is actually built-in, but certain are user defined. You can actually define how your stack is. Just stacking books, so you will stack it. So what we are saying here is these are like scalar quantities. Scalar is just magnitude, no direction. But these data types are like vectors. They have magnitude and direction. They have certain other extra attributes to it. Like you stack up something, or you put things in a queue, or you represent it as a tree. Data here, data one, there are certain connections are there. Or you put it in a graph, right? So there are certain, what you can see here is These are the basic structures using which almost all kinds of data that you have can be structured and fed into the system, where your programming language will understand the structure and then automate it. So your programming language is at the core here, and your programming language will not understand anything unless you define your information in these fundamental units. Now, under lists, there are different kinds of lists: linked lists, circularly linked lists, skip lists, many different kinds of structures again, right? So we'll cross the bridge when we have to. We don't want to do that, but this is a broad overview of data structures. There's another way to look at it. Let's say especially for Python, there's a way in which Python, being a high level evolved language, it has its own version of data structure and why it calls something the way or deals with certain information the way it does. Well, first thing is, of course, numbers. Look at you just think about, this is what you deal with, isn't it? Numbers. That's what everything is. You finally eventually want to reduce everything to numbers. So how does Python 3, the newer version of Python, how does it deal? It'll look at it as an integer, a real number, or a complex number. Under integral, it's got an integer and there are booleans. So it belongs to a class called int, and this one belongs to a class called bool. Now when I'm saying class, automatically what I'm trying to say is the entire Python is object oriented. Now this is a new way of looking at information. Everything is object oriented because everything is handled as an object, like a moving thing. So we will need a separate class on understanding object oriented programming and what is object oriented design, and what is the concept of making something object oriented, right? So you can go ahead and understand from other resources what it means. If not, do let me know. I'll bring in or probably record a good introduction to what object oriented paradigms are. So object oriented has a class. So there's a class of some event or a structure. So the physical or an instantiation of this class is an object. See, in simple words, it's like, I'll give you a simple example. Our human DNA is a class, and all of us are objects derived out of that class. So I hope that gives you some kind of a hint for you, right? Next, under integer, you have the int class, the bool class. Everything is a class, and eventually when you create a number which is of the class int, then you're making the link over here. So everything is defined. So everything is an object in Python. For somebody who's done a lot of C programming and the lower level programming, right? Those people will understand what it means when I say everything here is an object. For those who haven't done this, probably not ring such a bell, but it's okay, it doesn't matter. Okay, so I'm just telling you because I'm emphasizing the fact that it is object oriented. But for those who don't know, haven't done or dealt with the structures and programs in C, they will not be able to make the link of why we are stressing on the fact that. But the stressing of Python being an object-oriented programming right now has no bearing with you learning data science or the Python language itself. You will come to the appreciations of these kind of things maybe sometime later in your career, at the right time when you're ready to make use of that information. Well, Going forward, there is class float, then there is a complex class. Depending on the kind of number you're dealing with, there are certain attributes associated with complex numbers, which of course you need to have the value imaginary number I. So who holds that information? The class holds that information. What you can do with complex numbers is also held in the class. Now numbers are just numbers. What if there are sequence of numbers? So when there are sequence of numbers, we agreed that that is sequence is just like collections, right? So there are many kinds of collections. As we discussed earlier, lists are collections. Byte arrays, an array of byte are collections. Number of many bytes together are collections. Tuples are collections. But see the broad category in which they are categorized: immutable and mutable. Okay, immutable and mutable is just the fact which says that this class here can mutate. Mutate means you can actually ask it to mutate. You can take the same whatever you have declared and you can add more items to the collection and make it a new one. You have the ability to do that. That is mutable class, the mutable sequence. The immutable ones are once you define something, you cannot add it. You cannot just extend the same thing. So once you define the name as a string, like name certitude in your program, and if you make certitude as a tuple containing all these characters, later you cannot just use something like name dot append another word here, right? It will not allow you, because this is standardized. You've defined it as a tuple, so there is no mutation that it can happen, that can be done. So clearly you can understand that all your passwords, your security related protocols and everything should be immutable, because once you write a software, the only way you can change what has been embedded, let's say a feature or a variable called name itself, this always stays. Some other names like strings is a name, which, so we cannot have any string that doesn't make sense. Integer, it will not allow you to just remove the character called R in it, because integer will not make sense. These are immutable information, and it will be dealt with immutable collections. And those under those collections, types are strings, tuple, bytes. These are immutable. So hope you understand. Now there are sets, in which there are sets here, and there are frozen sets, which you cannot change, and there are certain attributes associated with frozen sets. So as you can see, nobody actually started a programming language in the beginning and then decided that let's have all of this. It is an evolved thing. As the complications and if different kinds of computations arrived, they started introducing different kinds of data structures. So we have just here now, so we need to know how it is evolved. Now there are types of collections with the set types. There's also mappings. You want to map some kind of information with another set of information, and there are certain memory constraints and how the mapping happens and how fast you can add some kind of key and a value. So if you want this value, you have to give the key. That kind of mappings in Python is handled by the dictionary class. So in other languages, you would have something called a hash map. In C, it's called a hash map, and in somewhere else, I think in some languages, you have a key value pair. Different names, but in our language of choice, which is Python, it is called dictionaries. Very much useful. Dictionaries are very much useful for data science. Now when all of this is set and done, there are certain callable classes, like you write a function, you write a method, you write a class. All of these are callable. Because when you write a big program, you would want that program to be structured, and you will structure those programs using functions. And inside a class, you will have certain attributes, like you will have, let's say, a class called employment data. You will have name and salary. So if there are certain things you want to do with the name and salary, you will write a function over here. Okay, and these functions are called methods. What and how you would want to compute it, those are all methods. And this whole thing is called classes. So classes themselves have many different kinds of classes. Okay, depending on what kind of things you can do inside and what can you do with the collaboration of different classes, all that has different. So classes itself is a class in which you'll have different kinds of classes. This is how the whole mega software is built. The next thing that Python gives us, or any language, in our case, let's talk about a collection of functions, methods, and classes. Those are modules. Now, all the best part of Python is most of the work is already modularized. You have many modules. Now, there are certain other things like you have libraries, you have modules, you have packages. Let's understand the difference or similarities, if there are any, so that we don't get confused while we're talking about it. Now, a module is a file containing Python definition, the functions, the variables, the classes, and the statements. That's a module. You want to write a new method or a new pipeline of doing things with a certain kind of data, like say you want to build a recommender system for your favorite music app. So a generic recommender system, if you want to make your code into a generic thing, you would want to see it as a module which others can add in to their software. So then it is going to be a file containing the Python definitions of all the things that you're in your pipeline. It's going to contain all the functions, the variables that you decide to use, the classes, internal classes that is required, all the statements, all of that packaged into a module. And a Python package is a directory, a folder of Python modules. So if you want a package which is going to do all your AI, now that package should be able to do many AI related things like recommender systems or linear regression or statistics. All of these are different modules, all packed, and that's a package. And a library is a collection of many packages in Python. And you can interchange, you can say a package or a library safely. You can interchange the references. You can use library or package, and there shouldn't be any debate on why you would call certain things as library or why you want to call certain things as a package and stuff. And this is not actually all that important, as long as you know how to do things and what and where things are found. But just to be right in terms of the technical terms used, I have added this particular piece so that you know the difference between the libraries, the modules, and the package. Of course, the library and a package is pretty much the same, and different modules together becomes a package. So it's something like modules many modules all together is a package. And in case you have many packages, you can pack them all in a library. So there are many AI related libraries like scikit-learn and stats model, stats packages. So You can change it's a AI package or an AI library. You can interchange uh, the words, doesn't matter. Okay, so let's talk about, I told you there are many kinds of programming languages, and what is Python? There is another kind of classification depending on how Python is understood by um, the the computing machinery, the hardware, right? So there are two kinds of languages. One is a compiled language and one is an interpreted language. A compiled language compiles a compiler takes the entire program in one go. So when you finish writing a program, the computation, it is going to be converted into an intermediate machine code and then computed at once, while an interpreter takes a single line of code at a time because it's in the interpretation mode. Here you compile everything, that's a compiler. It automatically takes everything, the entire piece of code that you've written, it's going to take everything, try to run it. If there is an error somewhere, it will find the errors and return, and it'll say, okay, there was an error, I could not compute. But an interpreter is going to run it line by line. First, let's compute this, see if everything is right, syntax wise, logic wise, the kind of data structure that is used, everything. And if there's an error, it will return the error here only. That's an interpreted language. The compiler generates a lot of intermediate machine code, while the interpreter never produces any intermediate machine code. There is no, there's no meaning for this, because anyway it is being computed line by line. There is no intermediate step required. The compiler is best suited for the production environment. An interpreter is best suited for software development environment. What does it mean? When you are developing a software, you are in a testing mode. You are developing an actual automation. You're testing whether certain automation can be done or not. Once you are ready and you think you have got the architecture, all the flows and everything right, then you would want to code this entire thing as a compiled program, because this one is for production. Because you are now, you know now that there is no logical error, there is no architectural error, nothing, there is no error, so let's put it into production. So this is deployed, and this one is in development phase. So you need that kind of an interpretation line by line, so it makes life easy. Now, for example, what kind of languages are compiled languages? C is compiled, C++, C#, Scala, Java, all of these are compiled. The languages that we are using is Python. It is an interpreted language. PHP, Perl, Ruby, and many others are interpreted languages. So when you, for example, if you take the source code, you write your code in Jupyter Notebook, there will be an intermediate step where you can look at it as if it's being compiled, but it is not actually in the sense of what a compiler does. There will be, once the source code is given, there will be an interpreter which is going to interpret it line by line, and for that there is a compiler. Okay, this is not that compiler. So we still want to call something which actually compiles this particular line and generate it into a bytecode. And then there's a Python virtual machine which has the knows and hows of what you have coded in your source code, depending on whether you put it as a list or a tuple or whatever it is that Python gives you. So it is going to check whether all of that has been properly structured, and it is going to take, if there are any other inputs which it requires while it is computing, it's going to take that input, and it is also going to take the support of the library modules that are attached to it. If at all you've called a library module like some recommender system here or some linear regression packages, if you have called, all of that will be here. It'll be if you say I want to use a certain numpy package to compute some numerical computation, and you declare something over here and send it, when it sees numpy, it knows that it has to take the numpy features from the library module. So the Python virtual machine understands all that, and it gets your code computed. So Python is an interpreted language. It is interpreted line by line. So you will see it in action. When it happens, you will see where and when the code error throws up at certain levels. Well, that brings us to a very interesting block layout here, which is a tree diagram of what you can do with Python. So let's just traverse it. So you have a list. So read it. A list are created using the syntax like this. A syntax for a list is this. Lists have what? Methods. So if you create any list of movies, then you can sort those movies. If you create a list of phone numbers or list of salary, height and weight, you can sort. You can also append some new items to those lists. These are the methods which are belonging to the class list. And another statement can be made about list, which is list are ordered groups of elements which are pointers, right? So all this pointers again is a different chapter altogether. You don't want to really worry about that right now. And lists are ordered groups of elements and can be of type. They can be a list of integers, list of strings, list of lists itself. Okay, so on and so forth. You can read lists are ordered groups of elements, can be modified by assignment. You can use, so there are certain syntaxes, you can use that, and you can assign or modify a certain value in your list. Let's say in your list called age, you had the third element as X. So you can modify this particular value in that list by using certain syntaxes. That can be done. Now, lists are also popular type of collections, and dictionaries, sets, arrays, tuples are also other types of collections. We have already understood that. Now, lists are iterated by loops. Iterate means what? If you have a list, and how do you know that if I say I want to change the third element from X to Y, so you have to write a loop which says go to the first, check if the one, go to the second, check if it is the one, go to the third and check if it is X is there. Okay, if you find X, then replace it with Y. This activity is called iteration. So they are iterated by loops, which often follow certain idioms. It means a structured inbuilt idiom, like for element in my list, right? There is a way in which Python understands that you are calling a loop. These are all idioms of that loop. So this, I'll share this with you so you can actually make the connection and get the idea in. This should start as the beginning of it's like a cheat sheet and of what things can be done, and this much is enough to start Python hands-on. Okay, so the next thing that we'll do right away is getting to the IPython notebook, and we'll start coding in. If there's need, then please look at this entire lecture again so that you can follow and see the flow of thought and get the complete idea of what computing actually is. Okay, hope you enjoyed. Thank you.